Hey, what's up YouTube? So I just wanted to just make a video just for some updates on the VibeCoder repo. So everything is now in individual markdown files. So if you're wanting to code up a program object, this is how you use it with AI now, is you have to upload all these individual markdown files and then chat with AI to make your program object. So a couple little updates from here, and something that I'm kind of personally interested in, and I think by far something on this repository that I've spent the most amount of time on, maybe 20 or 30 times the amount of everything else, is these optimal start logic blocks. It's all based off of a white paper. I'm actually I moved this to a separate, not the Niagara versions, but I've actually moved some Python versions to a different repository to just study the math behind these, because I think it's kind of complicated to understand. Even though the math isn't super complex, it's kind of complex concepts to understand. So this will all stay here, a couple of different models. So this is something I'm hoping to dive into a little bit more details, more about the theory running in the optimal start blocks. And yeah, maybe like a good time would be to jump right into some wire sheets. So if we would actually create like just a simple wire sheet, I'm just going to do something like testing. This is my office environment. So KitControl has their own optimal start block in the, let's see, where is it? I think it's in the energy section. So yeah, optimal start. So they have all these complicated math algorithms running in here too, and I complain that it's really hard to use. And the block is about 20 years old, I think. I can remember trying to get this to work in Niagara AX. And it's actually pretty hard. I set this up probably 10 years ago, and I swear I remember it working, but I'm having honestly a hard time making it work now. So that's when I ended up creating my own optimal start block. So let's just go back into, so if I navigate to my my repo here, I'm just navigating through my file system where I keep my my projects. So this is the bog files basically, which is the same thing. If you would go here on GitHub, and then you could actually find it here too. I'm just navigating through my file system because I have it on my computer, but yeah, so here's the optimal start, linear and quadratic, and then if you're on GitHub, you just hit this button right here, but I have it on my computer, so that's why I'm just navigating to it through my file system. So this is it. So this is the bog file. I have a running station here, so I'm just gonna copy it. I'll just paste it. Actually, hold up. I'm gonna go back into, let's see, where was I? I just want to copy the whole thing right into the, so I'm just gonna copy you. So I'm in my file directory, and then I want to go to my station right here, and that's here where I dragged this guy out earlier. So I'm just gonna paste you in right here, and maybe I can just put this next to you too so we can compare it. But like one thing, if you're ever working with these AI made program objects, remember you can always look at your application director and just to see if there's any errors going on in here. These are actually some log prints from some other project, but so this was no errors, so that's good. I always keep an eye on my application director. I can close you because I'm done with my file system. So this is the optimal start block that comes with Tridium. And this is compiled module, and then this is my program object that kind of mimics Tridium's optimal start block, but I think is a little bit more easier to use, a little bit more bells and whistles. Is about the same lines of code long in Java, which I'll show you in a second here. But one thing to note, so I'll demonstrate this on a live system, but there's, we wire in our zone temp. Same thing with here, the space temp, and they're using outside air temp 2 in their model. And then we always have to wire in, here's a schedule, a Boolean schedule that I'm using. So the optimal start blocks always require a next time and a next value. So that's the whole point of these optimal start blocks, is they need to know the schedule to operate the HVAC, like the next value and the next time. Because if we're unoccupied and the building is going to be occupied in 2 hours, that's our critical time that we want to be able to calculate how soon we'll be able to recover the zone temp to set point. So yeah, this is kind of, so if I was using Tridium's block, I would just wire in next time, next time and next value. And next value, and then they have this, they also have optimal stop. I'm not using that at the moment. Maybe someday in the future I'll think about it, but only optimal start. So mine, this is the whole point of it right here, is to start your equipment. So we're going to delete you because I think that block does not work very well, and just focus on the one that we made with the AI, and then based off of the theory inside, we can take a look at that too. So in the live system, we want to know the zone deadbands. So this is, so typically there would be a heat pump system or a VAV system or a VRF. The control system has like a zone set point, and then a deadband is baked in there behind the scenes. So let's say the set point is 72, which the building operators adjust, or the tenants, and then there'd be an occupied cooling set point of 72 and occupied heat of 68. So there'd be, so this is a 4-degree deadband right here. And this is a little bit of code right here that's actually calculating that. So this is, and then this block, there's a critical parameter called a temp tolerance that's just like a deadband. So the way that it works is we'll monitor the zone temperature, and then if the next equipment value is true, and there's a next time that we're calculating, continuously calculating how long it will take to recover that zone back to set point. So this target set point is we have it wired in for 70 right now, because it's actually calculating the deadband, and then it's taking the average. So like what you'd want to do is look for the control systems occupied cool and occupied heat, and then try and wire it right in accordingly, and then this will be the target zone set point is the actual set point that the operators pretty much adjust to, or the tenants. And if we're within the temp tolerance, that's the critical parameter that we're looking at. We need to get the zone temperature to the temp tolerance for these degrees per minute, heat and cool, to calculate. So I'll show you in the live system what this would look like, but so our schedule on the building automation system, we could be writing to it at priority 16, but the optimal start block writes to it at a higher priority. So if we're calculating that we need to recover the zone for warming up or a cool down, this will go true right here, and then it'll continuously tune itself. So right now it's in a null condition because it's not active at the moment. So if it's active, it'll be true right here, and we'll actually run the equipment earlier before the equipment starts. And then these are some parameters that we can talk a little bit about later. So this is like, there's code in the side here. That's a mathematical model. It'll use these degrees per minute to try and recover the zone, to calculate how many minutes it'll take to recover the zone. And it'll continuously tune these numbers. And then there's an output block that can be trended for the last run predicted minutes, and also last run actual minutes, because there'll always be a little bit of error, and then also last run minutes error. So it's basically the difference between these two. So this is something that should kind of tune itself and get better and better over time. All right, so enough about that. So this is actually a new Python project that I created to basically study the algorithms in a little bit more detail. So I'll call it the HVAC Optimal Start Math Playground. It's a repository to start for Optimal Start Mathematics and Python Learning Playground. And it's intentionally for people like myself with BAS technician background, so we only need to study basic algebra. We don't need to be a PhD engineer, even though like I think everyone should be involved, because maybe the PhD engineers could spot some kind of something wrong, or maybe we could be enhancing the tutorials in different ways. So it's for ordinary field technician people like myself to be, we need to know what we're doing, and studying like the theory behind this will only make us better at troubleshooting when it's not working. So there's a paper in here written by PNNL. So this is what all this work is based off of. There's a white paper written by Pacific Northwest National Laboratory, very smart group, PhD research people, PhD engineers that they've studied these different mathematical models, and then they've done some research to perform to know which mathematical model works the best. So this is one at the moment. I'm calling it Model 0. It's basically the classic linear model where we're just doing a degrees per minute. So that's what I was showing you earlier. There's actually Model 1, which is a quadratic regression going on under the hood. I'm using both of these in the Niagara program object world. And then these are some more advanced models that get a little bit more complicated, and you almost need some more complex math libraries, which Python has by default, but might be a little bit harder in a program object. So I'm not doing that. I'm only doing like the simple models in the program object. A little bit about these models: the Model 0, easy, medium, hard; Model 3, which we'll get into, and then according to the paper here, the PNNL study identifies as Model 3 as the most accurate overall. So you might get the best performance out of these, but only by a little bit. Model 1 still performs really well. Even the people that wrote this research paper told me that this is like a really robust way of doing optimal start. And then this Model 3, which does outperform Model 1 a little bit, incorporates weather into the model. So in essence, they call it they're self-tuning algebraic equation. So that's what we'll do. So this is actually little bit about the math going on here, which we can dive into. Some of the equations look a little bit intimidating, even for me. So there's this Python library called scikit-learn that we can do multiple regression with. And here's also like a little fancier logarithmic first order. So these mathematical models, they're running behind the scenes. So this is the stuff that this is what I'm hoping to do, is accomplish this. So I had AI create something really good for me, especially to do a crash course, to create a crash course so I can better understand how these mathematical models work. And I think it's I think it's really good stuff for people to know what they're doing. And ultimately, these are really big energy savings. Perhaps the best energy saving strategy is the optimal start. So, so I had AI create a 7-day course for each model. So 7 times 5, that's 35 lessons right there, 35 days, and then also a couple days of some more exploratory things that the P&L paper even describes as the latest and greatest math, and researchers still cannot figure out the Monday morning issue. So if you would ever notice, on a building automation system, I suppose you can show here. So on a building automation system, what the maintenance guys do is, if there's an office building that starts from 7:30 to 4:30, they always intuitively know I need to start my equipment way earlier on Monday morning, because the building sits unoccupied all weekend and it's really saturated. It could be really cold. Everything is really cold in the whole building. They'll take extra time to kind of warm it all up. So that's what they're kind of referring to, like extra, thermodynamic properties going on in the building. That the maintenance guys do this through intuition, but through pure mathematics and algebra, they cannot solve very well the Monday morning problem. So in my crash course, I put an extra day or two to play around with it. Hopefully I get to that point. And so this is what the maintenance guys end up doing, is they just, let's keep on running equipment a little more extra long. Pretty soon they start doing this, and now the equipment's running 10 times longer than it actually needs to. So that's this is why optimal start could be considered one of the most powerful algorithms if it's set up correctly, because it's low-hanging fruit. It's easy to do. If it works, it reduces the amount of equipment, runtime, which is directly correlates to energy usage. Okay, so this is week 1. We go over model 0. This is week 2, the quadratic model. Week 3, the weather adjuster, and then model 3 for week 4. And then week 5 is model 4, week 5 is model 4. And then there's also week 6 actually is a whole couple days of just playing around with the Monday morning issue. And then this is also just a link back to the Vibe Coder repo that we are actively testing model 0 and 1 in the field. So something that I've been kind of curious to play around with. Okay, so we have a whole bunch of information here on these models created from the paper, their descriptions and everything like that. And I even made an agents markdown. So this is token optimized, meant for the large language model, not necessarily the human, but it kind of gives the model equations. So what I was kind of curious to do is to upload a few of these things to AI, and then maybe we can talk a little bit about Tridium's existing KitControl library. So I'm going to go to my compiled modules here on decompiler.com, and I'm going to find KitControl. You can do this on any module. Essentially, you can go to decompiler.com and you can see what the code looks like inside. So this is behind the scenes in KitControl here. So right now we're looking at the actual Java code running inside KitControl. So let's go to HVAC, T-stat, psychometric, binary. Not actually. I think we have to go to energy. Here we go. Optimize start. And when I looked at this last, there was about 700 lines of Java running on the inside of it that kind of performs all these calculations under the hood. And if we look at our program object code, it's kind of doing the same thing. It's really similar. Not that much fanciness, I guess. Okay, so we're just gonna download this optimize start Java from Decompiler. We're just downloading it as a Java file. And then let's fire up. Let's go to ChatGPT. So I'm gonna just have it glance here at this. So this is Tridium's model built into Workbench. And then if I go to some of the stuff we know here, so I'm gonna go here. I'm just gonna start uploading some model context to AI. Maybe even give it the P&L paper. And maybe even give it, how about the agents markdown? So let's ask it, can you tell me how Tridium's KitControl model works compared to this Python HVAC optimal start playground and P&L's white paper? Curious how the KitControl models compare to the latest and greatest research. What kind of model is it? Okay, so this will have to marinate a little bit. Ooh, actually I found out right away. It kind of went scary fast. Okay, so here's the high-level summary. That's let's see what we got here. What KitControl actually does mathematically. KitControl uses a linear degree per minute model, which we also have as model 0, and this is identical to your model 0, linear model with an exponential moving average. So this is simply they're taking the temperature difference and kind of just creating a degree per minute and then adjusting it accordingly. So the KitControl updates its rates using its last warm-up period or cooldown. It would. This is the same method as model 0, so it only learns from one day after day. It ignores outside air temp originally, even though it has a slot to wire for that. So yeah, it'll also say that it suffers. So it's nearly identical to model 0. No surprise, because this is really old, outdated code. It only KitControl only learns from yesterday's performance, and then the models that we're using, even our model 0 has an adjustable parameter, so we can still kind of outperform KitControl's variation slightly because we're using the last 10 days of data. And then this is the more fancy models created by PNNL, that fancier math, which will outperform these linear models. So, wow, that was really fast how it read the Java code, and then it just can figure that all out. See, the power of AI. Okay, so we're done there. So something that I want to do is to kind of jump right into this. So if you want to join me in these lessons to learn the theory of optimal start, let's jump right in. So you might need to know just like a little bit of Python, and it's actually real easy. I'll just go over what it's like to set up Python, get it installed, and then it's actually a really friendly language to do some really simple math equations. The Java code that we saw on decompiler.com is that's a little bit more. It's a harder language to learn. It's a little less beginner friendly. But I'm going to stop this video here and then show you how to get set up on Python. And we can start diving right into our 42-day crash course. So we'll be jumping right into day 1 here shortly.